Hello everyone. Today we continue with the machine design and we are going to look at springs and see how we can use them when it comes to mechanical design or machine element design. So the learning outcomes for today will be we need to be able to analyze and design springs, and apart from that we need to differentiate the type of springs that are in use from day to day. So here is a picture of the springs that we have. So we have those as the pictures of springs. So since our learning outcome would be to analyze and design springs and differentiate type of springs, we need to understand what a spring is. And the spring is defined as the any resilient element that experience appreciable deflection without permanent deformation. And so, in other words, you can say springs are elastic members that deform under load and regain their original shape once the load is removed. And so, in design, the aim is to design a spring with the lowest possible weight that is able to fit properly into the actual application. And some of the applications that we use springs in, for example, when you are dealing with compression springs, these are designed to operate with a compressive rod and found in shock absorbers, in spring mattresses, mechanical pencils, and retractable pens. We also have what we call the extension springs, which are designed to operate with a tensile rod, and usually these are found in luggage scales and garage door mechanisms. We also have what we call the torsional springs, which are designed to operate with torque or twisting force, and they power every crosspin and mouse trap. Those from Eastern Province who understand the mouse trap. Okay, so these are the examples of springs. We have such springs as this, which we can find in shock absorbers, the mouse trap, etc., etc. So when we look at mechanical springs, their function are to exert a force, provide flexibility, and also store and or absorb energy. So in general, springs may be classified as wire springs, flat springs, or special shaped springs. And there are variation within these divisions. So wire springs, they include helical springs of round or square wire, and we're going to concentrate much on these helical springs. We also, and these same helical springs can be made to resist and deflect under tensile, compressive, or torsional loads. The flat springs include cantilever and elliptical types, wound motor or clock type power springs, and flat spring washers, usually called Bevel springs, and we're going to look at this also in details. Okay, so here is a look at the helical springs now. So helical springs are probably the most widely used, and helical springs may be used to support compressive loads, that is for pushing, or tensile loads for pulling, or torsional loads when it comes to twisting. So this is an example of the helical spring, and the equilibrium forces that the cut section, this cut section you can see here, anywhere in the body of the spring gets direct shear and torsional, and so we see that the distance from ear to ear, which we call distance d, this is the mean coil diameter, and this distance d here is the wire diameter. So when you isolate a section, like in this figure B here, for equilibrium, the isolated section contains a direct shear force F, this force F here, and a torsional moment T, and the torsional moment T will be given by the force which this helical spring is experiencing, multiplied by the mean coil diameter divided by 2. Okay, so when you look at torsional shear and the direct shear, here we have the maximum or inside fiber of a cross section, so your maximum shear will be given by this formula, and when you substitute these terms for maximum shear, you find that your shear will be reduced to this formula, 8FD divided by pi to the power 3 plus 4F, divided by pi to the power 2. And so this formula that we have here, we can now get what we call the factor out of the torsional stress. And from here, we can now define what we call the spring index, which is the ratio of the coil diameter and the mean diameter. So the spring index is simply the measure of the coil curvature, and the preferred value for the spring index will range between 4 and 12. Okay. This is also the shear stress correction factor, which we need to account for when it comes to the design of springs. So this shear stress correction factor will be dependent also upon the spring index C, which is the ratio between the coil diameter and the wire diameter. Okay, so from here, then you have what we have this equation here, which is the maximum shear stress for Erika Springs, given by this formula, where this case the shear stress correction factor, which is 2c plus 1 divided by 2c. Okay, so for the curvature effect, shear concentration type of effect on inner fiber due to curvature. And so if a spring is subject to ISI corroding at the wire cross section, the actual stress is slightly higher on the inside of the coil. This is due to the influence of the coil curvature and pitch angle. And so the influence of the coil curvature and pitch angle is what we are now going to look at, which can be ignored for static dark condition, but due to locality code working. Now, this can account for the effect by replacing the O factor or Bergresser factor, which can account for both the direct shear and the curvature effect. And so the O factor Kw is given by this formula. This will account for the curvature effect. We also have the Bergresser factor, which will also account for the curvature effect. And so this now the shear becomes reduced to this equation, encompassing the Bergresser factor, and then you multiply by 8, multiply by the force, and the dE. And concerning the curvature effect, to isolate the curvature factor, you are going to have that equation here, 10.6 from the recommended book. Okay, so the spring index C, which must be within 4 to 12, and the O factor Kw is in the range of 1.1 to 1.4. So this O factor will lie between 1.1 and 1.4, and the mid-range value for it is 1.2, and it's often selected as an initial estimate for KW spring design calculation, especially when you cannot factor out this one. And so the curvature correction factor Kc will be given by this equation, which will be the ratio of the Bergresser factor divided by this one which we found here, the shear stress correction factor, which is given by 2c plus 1 divided by 2c. So this is what you are going to have, and so this is going to predict the largest shear stress. And so what will predict the largest shear stress is this equation for shear encompassing the Bergresser factor. And so we are going to stick to this equation as we do spring design. Okay. So when it comes to the deflection of Erika Springs, the total strain energy for Erika Spring is composed of a torsional component and also a shear component. And so we are going to have a torsional component, a shear component, to get the total strain energy for Erika Springs. And to get that, we use what we call the Castigliano method to relate force and deflection. And so when you do the substitution, you're going to end up with your deflection being given by this equation here, and your spring rate being given by this equation here, which can help in the design stages of this spring. So the spring rate is also called the scale of the spring, and sometimes it's given by the force divided by the deflection. And that leads to this equation which we have here. Okay, so there are four types of ends usually used for compression springs. We have what we call the plane end, right hand. We have also what we call the square and ground end. We also have the square and the crossed end. We also have the plane end, ground, left hand. And so these are the four types. And to make use of this, there is a table which shows the formula for compression spring with different ends, which is table 10.1 from the recommended book. So if you have the end coil as plane, then the number of active coils will be n. If the total coils NT will be equal to the number of active coils. If your end is plane and ground, the total coils will be equal to the number of active coils plus 1. If it's square or closed, the total number of coils will be equal to the number of active coils plus 2, same as when it's square and ground. You can also use this table to find the free length of a spring. So if the ends are plane, then the free length of the spring will be given by this formula here. If the ends are plane and ground, then you have the formula for the free length being given as this formula represented here. For the solid length, it will be, if it's plane, it will be equal to this formula here. If it's plane and ground, it will be equal to this formula here, where this NT is the total number of coils. You can also find the pitch and all those things using this relationship here. And so that should not be a problem. And this D appearing in these formulas is the wire diameter. So you have the wire diameter there, the wire diameter even on the free length, the wire diameter on the solid length, the wire diameter also on that formula for the square or closed type of spring ends. So we can now quickly look at the set removal, which is a process used in manufacturing a spring to induce useful residue stresses. So presetting or set removal will increase the load carrying ability of springs in static application by increasing the spring's elastic limit. So to preset, all you have to do, the spring is coiled longer than its required free length and then compress to solid, causing the spring to set to its final desired length. And so this process will increase the spring's energy storage capacity to up to about 75% of the material's tensile strength. And this is common for critical springs made from premium materials. So the spring is made longer than needed, then compressed to its solid height, intentionally exceeding the yield strength. And this operation will set the spring to the required final length, and that yielding intelligence stresses opposite in relation to those induced in service. So about 10 to 30% of the initial free length should be removed, and so presetting is not recommended when springs are subjected to fatigue. We had looked at fatigue in the previous lecture, and so I'm sure everything is still fresh. Okay, for critical deflection for stability, buckling type of instability can occur in compression springs when the deflection exceeds the critical deflection, which we call Y critical. So with critical deflection, for buckling or elastic instability happens in compression springs during deflection, and this is due to the instability caused by a high slenderness ratio. And so because of that, it is as you compress the spring, the lack of stability causes the coils to tremble and shift. And so this can cause the load to create pressure on the shifted coil and plaster them, damaging the spring. So the spring slenderness ratio, which is the proportion of the spring's mean diameter to its length, is a spring's mean diameter. If a spring's mean diameter is more than 3 times its length, then that spring will tend to back when it's in operation. So then, therefore, the effective slenderness ratio will be given by this formula, and this value A is the end condition constant, and this end condition constant, we are going to see how you can get it from table 10.2 of a recommended book. And we have also C1 and C2, which are elastic constants given by this formula. And so we have C1 there and C2 here, which will be given by this formula. Then A, which we have as the end condition constant, and this end condition constant is given in table 10.2. If the end condition spring supported between flat parallel surfaces, the end constant alpha is 0.5, and if it's one end clamped, other end free, it's 2. So this becomes very important as you look at end condition constant, even as also you look at critical deflection for stability. This accounts for the way in which the end of a spring are supported, and so the end condition constant is given in these values. So for the values of alpha for other ND constraints included in table 10.2 may be used to plot additional critical deflection curves if needed. Okay. So we look now at absolute stability. The absolute stability occurs when this equation, the critical deflection equation, is greater than or equal to 1, and this results in the condition for absolute stability where you have this equation 10.2. For steels, this turns out to be equal to less than 2.63 T divided by the ND constant. Okay, so equation 10.10 for critical deflection, the LO here is the free length. Okay, now we look at some common spring steels. We have what we call the add-drawn wire, which is the cheapest general purpose, and we use only where life accuracy and deflection are not too important. So add-drawn wire, this is the cheapest general purpose spring steel and should be used only where life accuracy and deflection are not too important, and it's available in diameters of 0.8 to 12 millimeters. And this is not for use above 120 degrees Celsius or at sub-zero temperatures. We also have what we call the oil-tempered wire. This general purpose spring steel is used for many types of coil spring where the cost of music wire is prohibitive and in size is larger than available in music wire. Not for shock or impact loading, and it's available in diameters of 3 to 12 millimeters. But larger and smaller sizes may be obtained, not for use above 180 degrees or at sub-zero temperatures. So they are general purpose, and it treated for greater strength and uniformity of properties, and often used for larger diameter spring wire. We also have what we call the music wire. This is the best, toughest, and most widely used of all spring materials for small springs. It has the highest tensile strength and can withstand higher stresses under repeated loading than any other spring material. And this one is available in 0.12 to 3 millimeters. And it also has a condition you don't use above 120 degrees Celsius or at sub-zero temperatures. So these are higher carbon for higher strength. They are best, toughest, and most widely used for all small springs, and they are good for fatigue. Okay, we also have what we call the chrome vanadium. This is the most popular alloy spring steel for conditions involving high stresses that can be used with the high carbon steels and for use where fatigue resistance and long endurance are needed. And this chrome vanadium is also good for shock and impact rods, widely used for aircraft engine valve springs and for temperatures up to 220 degrees Celsius. They are variable in annealed or pre-tempered sizes of 0.8 to 12 millimeters in diameter. And so they are popular alloy spring steel. They have higher strength than plain carbon steel. They are also good for fatigue, shock, and impact. We also have the last one, the chrome silicon. The chrome silicon, this alloy is an excellent material for high-stressed springs that require long life and are subjected to shock loading. Local hardness of C50 or C53 are quite common, and the material may be used up to 250 degrees Celsius, and it's variable from 0.8 to 12 millimeters in diameter. So it's good for high stresses, long fatigue life, and also shock. Okay. Now we can look at strength of spring materials. Springs are manufactured either by hot or cold working processes. And this depends upon the size of the material, the spring index, and the properties desired. So we have what we call, when you're looking at the strength of spring materials with more diameter, strength is a function of the diameter. And so a graph of tensile strength versus what diameter is almost a straight line on a log scale, and the equation for this one is given by this equation 10.4, where A the intercept and M is the slope. We have the intercept and the slope. The values of A and M for common spring are also given in table 10.4 of a recommended book. So spring materials may be compared by an examination of their strength, and that I mean their tensile strength. And the tensile strength of springs vary so much with the wire size that they cannot be specified until the wire size is known. And so it turned out that the graph of tensile strength versus the wire diameter is almost a straight line for some materials when plotted on the log scale. Okay, so we have table 10.14, which gives us the values for the intercept and the values for the slope. For a music wire, the intercept value is 221 megapascal and the slope is 0.142. So this gives you the value of M, and this gives you the value of A, the intercept. Depending on the material you're working, if it's music wire, you use this one. Sometimes the material will be specified as ASTM number A228, which is still a music wire. AA229, it's OQ and T wire, oil quenched and tempered, had drawn, chrome vanadium, chrome silicon, etc., etc. And since we're using SI units, we'll consider the diameter in millimeters and the A in megapascal per millimeter. So this is the value of A that you'll be taking, and the value of the exponent that you'll be taking is this one, the exponent M. Okay, so we look at estimation, torsional yield strength. Since Erika Springs experience shear stress, shear yield strength is needed. Now, although the torsional yield strength is needed to design the spring and to analyze the performance, spring material customarily are tested only for tensile strength, perhaps because it is such an easy and economic test to make. So if actual data is not available, estimate from tensile strength will be used, and you assume that the yield strength is between 68 to 90% of the tensile strength, and so you have that relationship where the ultimate tensile strength and the yield strength should be related in that way. You assume the distortion edge theory can be employed to relate the shear strength to the normal strength. So you have your equation reduced to this one, and so this result in 0.35 SUT being greater than being less than or equal to this value, which should be less than or equal to 0.52 SUT. And the mechanical properties of some spring wires is given by table 10.5, where we have the music wire and we have the modulus of elasticity and all these properties which you can get as you look at this. And also for maximum allowable torsional stress, we have table 10.6, which gives us most of the things that we may need. For the music wire, we have the KS, KB or KW, the O factor of the ingressor factor at 45, and after set removal, this becomes between 60 and 70. Okay, so Erika Spring, compression spring designed for static service. You are going to limit the design solution space by setting some practical limits, and the preferred end for the spring index will be between 4 and 12, and the preferred end for the number of active coils will be between 3 and 15. And so for you to achieve the best linearity of spring constant, the preferred to limit operating force of a 10 to 75% of the force deflection curve between F is equal to 0 and F is equal to F. So the designer confined the spring's operating point to the central 75% of the curve between no load when F is equal to 0 and the closure when F is equal to the Fs, the spring force. Okay, so that's the maximum operating force should be limited to F max. And so your F max should be less than or equal to 7/8 of the spring force. So the limit of the maximum operating force will be given by that formula here. So then you're going to find that your fraction overrun to closure as this formula here, where you have this Fs given by this formula, and which will lead to this formula here. So when you solve for the outer equality of the fraction overrun to closure, then you're going to have such an approximation as 0.15, and so it's recommended that the value of this should be equal to or greater than 0.15. So quickly we can look at the summary of recommended design condition for springs. So we have said the spring index should lie between 4 and 12. The number of active coils should be between 3 and 15, and the factor of safety should be greater than or equal to 1.2 of a solid height for that spring. Okay, so now we can quickly look at figure of merit for high volume production. And so for high volume production, the figure of merit of form may be the cost of the wire, and so this figure of merit would be proportional to the relative material cost, weight density, and the volume given by this formula 1022. So the figure of merit now will be equal to minus relative material cost multiplied by all these values. And so you can now quickly look at the design flowchart for static loading. You're going to choose D if it's over a load, or free, or in a O. If it's free, then you're going to see if it's a AS wound or set removed, and you continue until you actually come up with your spring rate, until you also come up with a number of active coils, and then you calculate the form which we actually looked at. For design flowchart for static loading, you print or display DCOD form, build a table, conduct design assessment by inspection. You eliminate infeasible design by showing active constant, and choose among satisfactory design using the figure of merit. Okay, so finding the spring index for as wound branch. In the design flowchart to a branch with free as wound condition, the spring index is found as follows. So you are going to have this equation which will relate to a huge strength and the factor of safety, and you rate your alpha b equal to this and your beta be equal to this, where this we know it should be equal to or greater than 1.5, and so you substitute this equation B and C into this equation so that we can have a relationship which will be quadratic in C for the spring index, which will be given by equation 10.23. Okay, now quickly look at the critical frequency of Erika Springs. When one end of a spring is displaced rapidly, a wave called a spring surge travels down the spring. In the other end, if the other end is fixed, the wave can deflect back. And so if the wave frequency is near the natural frequency of the spring, resonance may occur, resulting in extremely high stresses. And because of that, catastrophic failure may occur as shown in the valve spring from an over-leved engine, as you can see on the figure on your right. So this was the catastrophic failure that occurred because of an over-leved engine. So there was valve springs which went through catastrophic failure. Okay, so for critical frequency of Erika spring, there are some equations, and so the equation that you usually use is the wave equation. And so the wave equation will have the spring rate, the acceleration due to gravity, the length of the spring, the weight of the spring, the coordinate long length of the spring, and u is the motion of a particle at distance x, and this is given by this equation 10.24, which is the wave equation. And so the governing equation for the translation vibration of a spring is this very equation. Okay, so the solution to this equation is harmonic and depends on the given physical properties as well as the end condition. So the harmonic natural frequency for a spring pressed between two flat and parallel plates in radian per second is given by this formula. And so in cycles per second or S, it's given by this formula. With one end against a flat plate and the other end free, it's given by formula 10.26. The weight of the Erika spring then is calculated using this formula, and the fundamental critical frequency should be greater than 15 to 20 times the frequency of the force or motion of the spring, and if necessary, redesign of the spring to increase K or decrease W. Okay, and when we look at fatigue loading of Erika spring, is a gentleman called Zimmery, who found that size, material, and tensile strength have no effect on the endurance limit of spring steel in sizes under 10 millimeters. And so the test found that the endurance strength component for infinite life to be when unpinned will be equal to about 241 megapascal or 379 megapascal. If it's pinned to 398 and 534 megapascal. And these constant values are used with Geber or Goodman failure criteria to find the endurance limit. And so the best data on the total endurance limit of spring steels, even up to now, are those that have been reported by Zimmery. Okay, for example, with an unpinned spring, the SU is equal to about 211.5 per square inch. The Geber ordinate intercept of shear will be given by this equation. And so for the Geber criterion, it will be that the SS is equal to 47.3 per square inch. Each possible wire size would change the endurance limit, since SSU is a function of the wire size, and so that must always be remembered. And it has been found that for polished, notch-free cylindrical specimen subject to torsional shear stress, the maximum alternating stress that may be imposed is constant and independent of the mean stress. And many compression springs approach these conditions, and so failure criterion is known as the Sines failure criterion. And so we can now look at torsional modulus of rupture, and this torsional modulus of rupture will be needed for the fatigue diagram. And lacking the test data, the recommended value for this modulus of rupture is 0.67 multiplied by the ultimate tensile strength of the material. From the standard approach, the alternating and the mid-range forces will be given by this formula, the alternating force being given by this and the mid-range force being given by this. And so the alternating and mid-range stresses, or the shear, or the alternating shear stress and the alternating mid-range stress will be given by this equation. We look at extension springs. These extension springs absorb and store energy as well as create a resistance to a pulling force. And these springs are normally attached at both ends to other components, and when these components move apart, the spring tries to bring them back together again. So these extension springs are similar to compression springs within the body of the springs. So to apply tensile load, hooks are needed at the end of the springs, and the common hooks that we have are the machine half loop, the raised hook, and the short twisted loop, and the full twisted loop. So we have 4 different kinds of loops. So when you look at the stresses in the hook now, in a typical hook, a critical stress location is at point A, and this is where the bending and axial loading given by this formula, the stress, and the bending stress correction factor for curvature will be given by this formula. So the great majority of breakages in extension spring occurs in the hooks, and so hooks are subject to both bending and torsional stresses, and these have higher stresses than the coils in the spring. So at critical section A, where bending stress and direct tension add, this critical point occur at the inner radius of the hook. So another potential critical stress location is at point B, as you can see, where there's a primary torsion, and we have that formula which we can use to find the shear stress at B, and so we can also get the stress correction factor for curvature being given as 4C2 minus 1 divided by 4C2 minus 4. So in hook design, this hook design reduces the coil diameter at point A, and so you have that as the force acting on this hook, and that as the force acting on that hook. So that's an alternative hook design. When we look at close wound extension springs, these springs are used to exert a linear force when being pulled. The coil of these spring types are kept close wound by initial tension, so the extension spring are often made with coils in contact with one another called the close wound. So when you look at this figure we have here, when you are looking at the total deflection curve offset by the initial tension Fi, so this is the initial tension. So if you are going to get this final tension, you are going to get your initial tension plus the spring rate, and you multiply that spring rate by the deflection. And so this includes some initial tension in closed wound spring up or the free length more accurately. So the closed wound extension spring are used to exert a linear force when being pulled, and the coil of this spring types are kept closed wound by initial tension. And these are some of the terminologies of extension spring dimension. We have a free length, which is measured inside the end hooks, and so the free length is given by this formula here. And then the hook contribute to the springlet. This can be handled by obtaining an equivalent number of active coils, and the number of active coils is given by this formula here. So here is an example of this spring. So we have the hook here. So this is the hook length, and this is the loop length. We have the wire diameter, and we have the inside diameter here, and here is the length of the body of the spring. And from the end of the hook length to the end of the loop length here, this is what we call the free length. And so we have the outside diameter, and we also have the mean diameter. Okay, so the initial tension in closed wound springs, we have the initial tension which is created by twisting the wire as it is wound onto the mandrel. And so in the spring industry, the term initial tension is used to define a force or load which places the coil of a closed wound extension spring against one another. And this force must be overcome before the coils of a spring begin to open up. So initial tension is wound into extension springs by bending each coil as it is wound away from its normal plane, thereby producing a slight twist in the wire which causes the coil to spring back tightly against the adjacent coil. So this initial tension can be wound into coiled extension springs only, and the hot wound springs and springs made from annealed steel are hardened and tempered after cooling, and therefore initial tension cannot be produced. So when you remove from the mandrel, the initial tension is locked in the end because the spring cannot get any shorter. So when you look at this graph here, which showing all these processes happening, so the amount of the initial tension that can routinely be incorporated is shown on this graph. Okay, and so the two curves bounding the preferred range is given by this formula here. So this formula gives what we have, the two curves which are bound by this preferred range, and so that is what we have. And then from table 10.7 we can get a guidance for maximum allowable stress depending on the material. So the recommended maximum allowable stress corrected for curvature effect for static application is given here. And so if the material is the the steel and non-ferrous alloys or austenitic stainless, then if the torsion is in body or end, those are the percent of tensile strength that we have. So you can relate the percentage and then calculate the required value. So the helical coil torsional springs, these can be loaded with torsional end rods, as can be seen. So we have special ends, we have short hook ends, we have hinge end, straight offset, straight torsional, and the double torsional. For special ends are used to allow a force to be applied at a distance from the coil axis, and usually used over a rod to maintain alignment and provide buckling resistance. And for end location of torsional spring, the terminology for locating relative position of ends is shown. Here is the graph that we have. So the initial unloaded partial turn in the core body is given by this formula, where NP is equal to beta divided by 360, and that angle beta there can also be calculated when you've been given the partial turn. And the number of body turns, NB, will be full turns plus the initial partial turn given by this formula. And we can get some of these tolerances from table 10.6, where the total coil is up to 3, then the tolerance per degree will be plus or minus 8. Same applies to for helical torsion, coil torsion, or spring for the coil diameter and the spring rate ratios. Okay, so for the stresses in torsional springs, we still need to make use of the stress formula here, and when you find the stress, then you need to find the stress correction factor at inner and outer fibers that can be given by these two formulas. For the inner fiber, you get this formula to find the stress correction factor. For the outer fiber, you get this formula to use to find the stress correction factor. And so this stress correction factor for the inner fiber is always larger, giving the high stress at the inner fiber. And with a bending moment, then the bending stress will be given by this formula, where the stress concentration factor at the inner fiber plays a critical role. And so the angular deflection is commonly expressed in both radians and revolutions per turn. And in terms of, if a term contains the revolutions, then the variable will be expressed with a prime sign. So we have this, the spring rate with prime sign, which is linear, and expressed in this formula here, where this is the moment, and it can be expressed as either FL or FR. Then, using the Castigliano's method to find the deflection radian of a body torsion, we have this formula here, and then when we have the moment and integrate over the length of the body, we have a formula which reduces to this one. And when you're using I for around Y and solving for Q, that becomes our final equation. And so the deflection in the end of the spring must be accounted for, and then you need to get the angle subtended by the end deflection, which is obtained from that formula here. Okay, so the total angular deflection is obtained by combining the body deflection and the end deflection, which is given by this formula. And remember, when designing your torsional springs, the wind direction of the torsional force is critical. So you will need to know whether you have a flat hand, or if you have a left hand or right hand torsional spring required for your design. A left hand spring will generate torsional force in the clockwise direction, while the right hand spring will generate torsional force in the counterclockwise direction. So having the incorrect direction of wind will result in a non-functional torsional spring. So make sure when you're designing those, you know the direction and what you want to achieve at the end of the day. And so from there, you can now get the equivalent number of active turns, which will include the effect of the ends, which is given by this formula. Okay, so spring rate in torsional springs. So the spring rate in torque per radian will be given by this formula, and in torque per turn, the spring rate will be given by this formula here. And the only difference between the two is for the torque per radian, it's at this 64, and for torque per turn, it's just 10.2. The rest remains the same. So to compare for effect of friction between the coil and the handlebar, the test show that 10.2 should be increased to 10.8, and so this becomes the spring rate in torque per turn to compensate for the effect of friction. And when you express this equation, which we use to get the total number of deflection, it will now give you the spring in revolution, and applying the same correction for friction, it will give you the total angular deflection as given by this equation. So if you decrease the inside diameter, the torsion spring under load will experience a change in coil diameter, and if a spring is over a pin, the inside diameter of the coil must not be allowed to decrease to the pin diameter, and so the angular deflection will be given by this equation, and the new Erik's diameter will be given by this equation. This will be as deflected coil, and then the new inside diameter will now be given by this equation here. The diametrical clearance will also, between the body and the coil, will also be given by this equation here. And when you solve for NB, this should be the final equation that you need to have. So we move from here to this final equation, and this gives the number of body turns inside to assure a specified diametral clearance. So to obtain the normal yield strength for spring wires loaded in bending, you are going to divide values given to torsion in table 10.6 by 0.577, and this is using the distortion energy theory, and by so doing you are going to get these values. For a music wire, it's 0.78 multiplied by SUT. For oil quenched and tempered, 0.87 multiplied by the SUT, and so on and so forth. For fatigue strength for torsional springs, the science method and Zimmed data were on for torsional stress, so are not applicable. So lacking better data for endurance limit in bending, we are going to use this table here from associated spring for torsional spring with repeated load to obtain the recommended maximum bending stress. So for fatigue life cycle, if the fatigue life cycle is about 10 to the power 5, then not short pinned, it will be about 53 if it's ASTME A228, which is a music wire, or if it's the other type of material that has been used. So we're going to get this so that we get the associated spring for torsional spring with a repeated rod, and we're going to obtain the maximum bending stress. Okay, so the next thing that you do is you're going to now apply the Gerber criterion to obtain the endurance limit, and you need to always be aware that the repeated loading is assumed on this condition as you look at the Gerber criterion to obtain your endurance limit for fatigue strength for torsional springs. So this will account for corrections for size, surface finish, and type of loading, but not for temperature and miscellaneous effect. So applying the Gerber criterion as usual from table 6.7 with the slope of a rod line, then we are going to have the factor of safety being given by this formula here, and you can get NF direct from table 6.1 using this formula. And so the next thing that we can now look at are the bezel springs, which is a cone disc spring with unique properties. It has a non-linear spring constant, and this spring can be used for snap acting mechanism, and so on and so forth. So those are what we use this bezel spring for. So it can be used for snap acting mechanism and also provide the constant load for a considerable deflection range. So this, according to this graph we have here, we have the rod and the deflection, and we have the ratio here, which must be greater than or equal to 2.83 of this S curve, and it can be useful, as you can see. For constant force spring, the extension spring shown is made of slightly curved strip steel, not flat, and the force required to uncoil it remains constant, known as the constant force spring. So we have the rated rod, the initial deflection, and we have that value here, the dimension, and the inner diameter here, and the force acting here. For the conical spring, this is wound in the shape of a cone, and so we have this force, the spring force acting on here, we have this diameter here, and we have this distance R2. So mostly these are compression spring made with a round wire. The principal advantage is that the solid height is only a single wire diameter. Okay, so we can now look at the volute spring, which is a conical spring made from a wide thin strip or flat of material wound on a flat so that the coil fits inside one another, as you can see from this graph. Since the coil do not stack on each other, the solid length is the width of the strip. So a variable spring scale is obtained by permitting the coil to contact the support, and the deflection increases in compression, the number of active coil decreases. So when you increase when the deflection increases, the number of active coil decreases. For constant stress cantilever springs, a uniform section cantilever spring made from the flat stock has stresses which are proportional to the distance x here, and so we have the force F acting at this point, and we have this length of the cantilever and the stress being given by this equation here. And when you look at these two figures, it's often economical to proportion the width be this one to obtain the uniform stress independent of that distance x. For a rectangular section, the IC will be equal to BH squared divided by 6. And when you combine the equations that we have, we end up with this equation. And from this equation, you can make B the subject of the formula and solve for it. So since B is related to the distance x, this one, the width BO at the base is equal to BO F 6 multiplied by the force F multiplied by this length divided by the H squared multiplied by the stress. And so when you apply the Castigliano's method to obtain the deflection and spring constant equation, the width becomes the function of this distance x, and so this B becomes equal to O multiplied by x divided by the L, the distance of or the length of this cantilever beam. So what you're going to do is now you're going to integrate the Castigliano's deflection equation with the moment and both function of this distance x, and so your deflection then becomes equal to this formula here. And from here we can get the spring constant as equal to BOH3 multiplied by E divided by 6L to the power 3. So that's what we had for today on springs, and I hope it helps on one or two occasions. So next time we'll receive an assignment and see how we